Good. We can see you now.
Yes, thank you. And I'll share my slides as well. All
That
right.
works. That works.
Yes, thank you. Yeah, thank you for giving the opportunity to share our technology. It's still in the early stages. So we are located in San Diego. I have been in San Diego for the past 17 years. I came here for PhD and stayed here. I did my PhD at the University of California, San Diego, and have become a San Diegan. And this technology that we are working on since 2020, and now so basically we are in the lab prototype stage. So we have finished the proof of concept of the concept itself, and which I'll share in a bit. Okay, I will start. So essentially, what we are doing is so battery has different components: anode, cathode, separator, electrolyte. What we are trying to do here is to change the geometry so that so we can expand the capabilities of these materials can do. And since Volta has first like done the voltaic pile, so pretty much like the concept is still remains the same. So and we thought about it by bringing the nanotechnology into the picture and how we can improve the current energy storage devices. So that's how we started. So my expertise is basically nano-engineering. I worked on the interface of material science, chemistry, and electrical engineering and physics. And basically this technology tries to achieve that by changing the geometry, improving the battery specs. So this is based on our initial proof of concept studies. We are building our first prototype, lab prototype. So it's in the coin cell format, and based on our initial test, this is what we expect. So essentially, one of the important features that is achieved by our novel geometry is fast charging rates. So right now we aim to achieve like 15C, so which corresponds to about like a few seconds charging and discharging. Essentially, this brings that the limitation is not the battery itself; it's essentially the current source. So it basically reverses that, and we believe that we can improve this even further. And higher energy storage is the other aim we are trying to achieve. So in the first prototype in this current chemistry, so we plan to achieve more than 1,000 watt per kilogram. And this is not a so one of the issues with the novel technologies is the cycle life. How many cycles you can do. I mean, even in extremely high energy density, if you can go only like 10 cycles, it doesn't really help. So in our current test with the materials, so we believe we can exceed well over 1,000 cycles. And while we are doing this, so we don't expect that we will compromise safety because of the things that improves, especially charging, is also comes back with the benefits in the safety as well. And one of the things is because of our geometry, so the battery can be built in any shape. That we especially we have a lot of traction on the aviation side because because of the shape, so we can fit it in different settings, and so this won't be a premium technology because of the energy density and we being able to do like quite thick cells. So we believe that we can actually be quite cost effective. Essentially, here our starting point was the dendrite problem. On the left-hand side, you see the conventional battery geometry. It's like you can call it. Some people call it like sandwich assembly, cathode separator and anode. So cathode is made up of nanoparticles. Essentially, it's called slurries, small nano and micro nanoparticles of cathode material, and with some carbon black in between to improve the conductivity, and with some polymers. to kind of improve their attachment to each other. And the separator is like a film, pretty much. And the anode is also a porous material. And right now there's a trend going towards silicon because of its high theoretical energy capacity, which it can hold a lot of lithium ions. Right now, the issues with that is like you can imagine that the current battery geometry is like a city is connected by a bridge. So essentially, like think about New Manhattan and Brooklyn connected by a bridge. So we have all the roads that Manhattan has that connects. So imagine like all the people living in these cities are basically lithium ions. So there are a lot of roads that connects their houses, and they can get out and they leave their houses. But eventually, all the roads connect to the bridge, and now you have a traffic congestion at the bridge. So you slow down at the bridge, so there's a lot of traffic at the bridge. So then once you pass the bridge, so now like you have all the other roads that takes you to anywhere you want to go. The problem is, even if you improve the porosity or if you change the energy density, essentially you can make like more skyscrapers in Manhattan or like more roads everywhere. It doesn't really help on the bridge. So you need to make like more bridges, but the bridge is essentially we are basically physically limited. So what this leads to is high energy, high current density. So usually the magic number for current density is 6 milliamps per centimeter square. As you see, it's about like the surface area that they are kind of exposed to. It's not an exact number. It's roughly over 6 milliamps per centimeter square. So you start to see like very fast dendritic formation, which is essentially lithium start interacting with each other, and it's a process called electroplating, and they grow this kind of crystalline structures, which eventually shorts the anode and cathode. So right now that is the main limitation. So that's the reason why we cannot charge really fast. So because at some point, so the ion current density increases so much, so then the dendritic formation becomes out of control. Then once you short it, so then you basically break the battery. We try to keep this ion current density by slowing down the charge and controlling the basically the porosity and essentially electrolyte formulations and then the ionic conductivity in the separator. So all these parameters, the ionic conductivity of the cathode and ionic conductivity of the anode, electronic conductivity of everything kind of contributes to this problem. So it needs to be balanced quite well. So, and essentially, and dendrites being kind of like the bottleneck, so it affects like all the parameters. So it affects cycle life, so it leads to capacity fade. To basically reduce these effects, we try to change the chemistries, and the chemistries become even more complex. That leads to side reactions, that leads to precipitation, and it's a chain reaction of events. So what we are trying to do is essentially in this Manhattan, Brooklyn, and instead of like having people pass through a single bridge, so essentially we are just giving them bridges, so every single one of them. So essentially increasing the surface area so much that the ions don't really meet with each other. The way we do that is essentially start with a kind of porous anode, but pretty much like the coat pores of the anode with the separator, so now in submicron thickness, and distribute it all over the interface, and then fill the pores with the cathode material, as you see on the left-hand side. We still have anode, cathode, and separator, but now instead of like they are being on the side like a sandwich, it's more like they are embedded. We call this EMELA, it's embedded electrode assembly. So if you go towards, so these three-dimensional anodes have been studied before, but now like we are talking about a feature side that is in the submicron level. So that improves the surface area extremely. So this has like two main benefits. One is again the surface area, and here I'll just go back a few slides, and here, so what we are trying to improve is here is the centimeter square. So if you improve the centimeter square, so then you can really do ion current density quite a bit. so then you can stay well below dendritic formation threshold. That gives the opportunity to even like charge much faster. We are talking about hundreds times faster. So one is the surface area improvement. The other is also, since they're embedded, the distance that ions travel becomes shorter. That helps with the ionic conductivity of the entire cell. So that's the bottleneck. So one is the surface area of the interface. The other is the ionic conductivity. And by reducing the distance that ions travel, we also improve this. So we rely less on the improved ionic conductivity of the material, because the distance that the ions travel is from several hundred microns. Now it's reduced to a few microns. So in that sense, there is about 100-fold reduction in the distance that ions travel, and also there is more than 100-fold improvement in surface area, which brings down the ionic current density. So we call this PINC because it's like almost like parallel integrated nanocomponents, in a way that so now on the left-hand side you see a quite heterogeneous cell structure. So if you put like a pen anywhere, so you either meet a cathode, separator, or anode. But if you go to this chemistry, so if you have like these small boxes, so pretty much you have all the components, anode, cathode, and separator. So you turn the heterogeneous cell structure into a more homogeneous cell structure. It's almost like you have this micro-sized batteries, even like sub-micro-sized batteries that are connected in parallel, that looks as a whole. But in the end, you still have like one current collector one anodic and one cathodic current collector. Everything kind of goes back to the same thing. So essentially, to achieve this, so we need to bring the cathode grain size to smaller, which we have been working on for a while, which we achieved on multiple different cathode chemistries. Separator is a proprietary. This is what it enabled. As actually, this is the key part here. So this is a hybrid organic inorganic material that we can directly coat on the anode pores. And the anode, we are using silicon for this current chemistry. It is the current geometry is not limited to silicon, but we like silicon because it provides high energy density and ease of production. So we are basically borrowing some semiconductor processing techniques that is used in solar cells and actual chip industry. That's how we generate our anode, and we directly apply our separator on it. We just directly grow on it, and then essentially bring the cathode and then achieve the assembly. So this brings us in this point. So this is the famous energy density, power density curve that we are already memorized. The capacitors is like very fast discharge rates, so that brings their power density quite high. But this is logarithmic, but as you see, energy density is quite low. That's why we don't prefer to use them as energy storage devices, but more like complementary devices for different applications or completely different applications. The conventional lithium-ion batteries, in terms of energy density, they are quite high, but they lack the power density. You see some example companies. Essentially, most companies are basically lay on this. I pick Ampersand and QuantumScape because like one of them goes for the separator, the other for the anode, and the other for the electrode. So essentially, different components of it. But Holy Grail is the top right corner, and that's basically by first improving the power density, and then we believe that we can improve the energy density even further by basically implementing our geometry in different kind of chemistries as well. And in terms of application areas, so we believe this can be used in many different application areas. I mean, from consumer electronics to aviation. We have a lot of traction in the aviation side, but of course, like EVs and consumer electronics are other hot areas. The other is electrical energy transport, essentially making like large scale batteries, almost like as big as like container size, shipping container size batteries that you can kind of ship with trucks, with actual ships and as well as like trains. So essentially like making the electrical energy transport like almost like petroleum, where you can produce anywhere, but you can transport the energy itself to somewhere else in the world. So that's the other energy areas, the other areas that we got traction from, because of like while improving the power density as well as the cost and as well as fast charging rates are the areas. I don't need to tell anything about like how big the industry is. I'm sure like everybody in this group will know really well. So in that sense, right now, our current approach is to make our first lab prototype, have it tested, and confirm the specs that we are trying to achieve. And right now, so we are also like talking to manufacturers that we can partner with. So we want to at least like keep the assembly to ourselves because of the like the specific kind of separator processing, but the other components can be contracted out. And basically this is the end of my short presentation. Thanks for your attention, and thanks for giving me the opportunity to present in the Green Connections.
Thank you a lot, Inanc. How do you pronounce your first name?
Inanc, like CH at the end.
Okay, very good. I hope to see you in person anytime soon.
Yeah, thank you.
Have a couple of questions here. What are the big trends in battery technology? Your colleague Larry gave a presentation for Cleantech San Diego, and there was a lot of different battery technologies, but more with graphite and sodium and things like that. Are you alone in this field with the nanotechnology?
No, actually, we are not. But overall, I mean, so right now, in the current kind of geometry, so we kind of reach to the limits of what you can do. Essentially, like improvements of 10%, 20% is called kind of revolutionary in a way. But what we are trying to achieve here is, so if we propose a new different geometry, which you can still utilize the current materials and also expands the opportunities, can we kind of exceed the specs? So in that sense, we don't see ourselves as like a direct competition to the industry in general, but more like a new platform. And so basically, we are already start talking to some cathode manufacturers themselves that basically certain things can be applied to our geometry. And also we are trying to improve our silicon processes, but there is also some alternative materials that we are exploring as well. So in that sense, when we kind of change the geometry, so now the current materials can be applied to this, and then also improve the specs. But for our case, so another trend is also like going solid state, which our current chemistry and our actual separator chemistry is compatible with. For our first prototype, so we want to solid state, so it will be a liquid phase. But eventually we want to move towards solid state, which we believe that it will contribute further to the energy density and safety as well. And alternative ions are also compatible. But right now, I mean, one of the issues with the lithium alternatives is like one of them is like the density formation. And safety issues. We believe that our geometry can address some of it. So in that sense, it can expand the life cycle of lithium. So then maybe alternative ions that we are not exploring at this point. But I mean, having said that, so we are basically open to using. So overall, in our presentation, as you see, I didn't really touch too much on the chemistry aspect of it. It's more like the geometry aspect of it. So we believe with this new geometry, we can utilize the current chemistries as well as new chemistries, and we can expand the horizons a bit further.
Okay, so when do you think you have your first prototype in operation? If you make an educated guess.
So we believe as soon as like mid next year.
Next year, okay.
Like a functional prototype that we already have started testing the half cell already, and some of those specs that I was talking about comes from our experimental studies. But now we are optimizing the process. So right now the key point here is, So making the prototype and just like charging it doesn't really help. So we want to like make it, so it won't be a commercial prototype. So but we want to make it as close as like in a manufacturable form so that we can expand. So in that sense, we are still going through some optimizations, but we believe as soon as next year, we will have a functional and third-party test prototype. That's the goal.
That's very nice to hear. I hope to have you back here on Green Connections next year.
Thank
And
you.
that you have made some progress.
Yeah, thank you. I appreciate it.
Thanks a lot. Maybe you turn off your video then and your sound. Thank you.